No? Okay. I can't really hear you. Sorry, the sound is really bad. Okay. Your sound is, I can hear you a little bit, not much.
Okay. All right. So, hello. I believe everyone should be hearing me now. Okay. Let me just switch here. All right. Hello, everyone. Welcome to this live stream. Thanks once again for joining in. And I'm going to briefly introduce the live stream, of course, and everything else that you need to know about the live stream, and I think we go on from there. So if you can't hear me, you let me know in the comment section, and the moderators will take care of that. So I have my second screen here, so I may not be looking directly at the camera. So yeah, today's agenda, while you're here, you of course you get to know what you learn, and get to know the hosts, the philosophy behind our programs, and so on. So I'm just going to run through that. So why are you here today? Of course, you're here to learn about the latest trends in machine learning and artificial intelligence, data science, and so on. So that's one thing you get to learn today. So get to learn from Dr. Sebastian Raschka. I'll introduce him. at the end of the slide. So first off, the advice for beginners in ML. Please, if you're a beginner and you're attending the session, we have 3 tips for you, really, for you. So you should take note of terms you don't understand, research on those terms, and engage with the community on social media tasks. So just pretty much take note on terms you don't understand, and research on terms, and engage with the community on social media. Take home the best practices and for good methodologies. So of course, what you learn, of course, you learn about the latest trends in AI. You learn about the latest techniques, the biggest developments in the space, of course, and every other thing that has to do with career, advancing your career in the space of data science, machine learning, and artificial intelligence. Yeah. So of course, we host our Port Harcourt School of AI. You can check us out at our community website, phdschoolofai.org. And I think everything else can go on from there. Of course, while we do this, you can also check us out as well. What we do as well is on Twitter. All right, so sorry about the break. I was just addressing Doctor. Yeah. So who we are, of course, we're a non-profit social organization whose mission, of course, is to build competent and collaborative AI and data learning community to solve societal problems. So that's what we are. I'm going to just run through this briefly. We are in River State, Port Harcourt, Nigeria. Of course, what we try to do is to make River State a data-driven state and a hub of competent and collaborative AI talents. Yeah. So, of course, what we do is we try to make sure that we ensure inclusive education in the space of data and artificial intelligence technology. So, whether it's education, whether it's accessibility for the technology, that's it, right? So, our story so far as well, you can read us on Twitter, PhD School of AI. You can follow us on Twitter. We have our report from last year. Of course, let me just turn on my pointer here. So, this here is our report. You can, of course, take a screenshot of that and it's available in the description as well. So, philosophy behind our programs, we believe that for every program we run in Port Harcourt School of AI, we can actually be leaders and enable empathetic problem solvers. That's why we try to bring experts behind our programs to make sure that their members that are enrolled in the program are getting the very best. Yeah. So, but yeah, this is about it today, and I think after the session today, I think where you should go from here is we expect that you join an AI learning community in your region. Explore more topics for today's sessions, like clicking the links in the description. Get started if you haven't in machine learning. Of course, if you're interested, of course, then go on Twitter, ask experts. There are lots of experts in the space. The general AI community members, they are willing to. It's a very very accessible community. So of course, there are lots of communities. If you're in Nigeria, there are lots of communities. In Nigeria, you have Data Science Nigeria, Port Harcourt School, yeah, of course, AI Saturdays, and so many other communities. Just Google, really, out there. Right? So you can join us, PhD School of AI, on Slack. These are the links to join us there. But I'll just go on. Without further ado, I think we can know our facilitator for today. Our facilitator is Dr. Sebastian Raschka. He's the assistant professor of statistics at the University of Wisconsin-Madison. And of course, he's the author of the popular Python machine learning book. And I think it would really be amazing to learn from him today. So I'm just going to hand over right now to Dr. Sebastian, who has done amazing work in biostatistics the world over, and of course is one of the very best experts or experts inside in the AI and machine learning space. So without further ado, I think I will hand over to Dr. Sebastian Raschka. Yeah. All right, Doc, I think you can comment.
a lot of slides. I hope I haven't made too many. I will try to get through most of the interesting ones, but if we don't get to everything, that's fine. I think we have 45 minutes as far as I know. But with that, let me get started then. So most of this is based on, somehow it doesn't let me forward. Okay, there we go. So most of this is based on a paper that I wrote with two co-authors, Joshua Peterson and Corey Nolet, who work at NVIDIA. And we had this very productive January where we were reviewing all the recent trends and were having a lot of discussions about that. And this is a pretty long manuscript. I think it's about 40 pages, 45 pages, something like that we ended up with. And if you would like to read all about this, so you can find the article here under this link. But yeah, I will only give you some snapshots from the paper. I will not go over everything here because it's also a little bit technical and a little bit dry. So I try to focus more on the interesting parts that have nice visuals here in the slides. So the first part is about the technologies and tools that we use in machine learning and deep learning. And a lot of things have changed in the recent years. So this is a University of Michigan in 1960 or so. So you can see back then the tools were quite different compared to today. So today we have usually small laptop computers, but also we have very fancy workplaces with where you can walk during working even. I'm not sure if that is even something I would want to, but yeah, you can see things have changed a lot. And also as a professor, I try to keep up to date with the technology when I'm teaching, because I remember when I was a student, I had to use MATLAB, which I didn't really like. So I try to be nice to my students by also showing them tools that they will actually use later on when they apply for a job. Something like Python, for example, TensorFlow and PyTorch, so more like the most recent packages. So usually when I start teaching about machine learning and deep learning, one of the first things I explain is that using for loops in Python is actually quite bad if you are doing scientific computing or machine learning and deep learning. Usually that is helpful for maybe debugging or implementing your first functions, but it is very slow because Python doesn't have multiprocessing by default enabled or multi-threading, so we would have to do something on top of that. So by default, this for loop would run iteratively. So that is a case where we execute something one at a time. So if we have this function here where I'm computing z, and z could be the net input in a perceptron, a logistic regression, or multi-layer perceptron model. So these are usually the weighted inputs. So you have a couple of feature observations, like the xi's, and then you have some weights. So you compute the weighted input and then add some bias units. So if I would draw that, it would look something like that, where I have some output and these are my x's. So I have x1, x2, x3. And for each x, I have a weight parameter. And then I compute the sum here. And then usually I also add a bias unit to that one. I can implement that as a for loop. And I think that's a good exercise if you want to make sure that everything works correctly, because implementing a for loop is usually very easy for programmers. But then usually when we implement deep learning code or machine learning code, we use linear algebra because it's not only more, I would say, concise if we write this as a mathematical notation, but it's also more efficient in code. And that has something to do with how these things are implemented. So NumPy uses a lot of efficient C++ code under the hood, and this is also something that makes use of the linear algebra libraries that are already on the computer, which have been optimized for the processors to compute this very fast. So for the, if I go back one slide, for this computation here, I have three things that I sum up here, and I don't have to wait for this one to finish before I can compute the next one here. So I can compute all of them in parallel, and then I just have to sum them up. Now imagine, here it's maybe trivial, but now imagine each of those is a very expensive computation. So this one and this one, these are very expensive computations, so I could technically compute them in parallel. So these could be, each of them could be, for example, a large dot product itself. So in practice, we would, for example, use dot product here between the two vectors to compute the weighted sum. And that is much more efficient than just using the for loop. And Especially when we do this on GPUs, there's a huge advantage because GPUs have a lot of cores, processing cores. So if we have large computations that can be parallelized, that's really where GPUs come in. But before we talk about GPUs, let me just show you a benchmark where I compared these two functions. So at the top, I was running the for loop. So this is just a benchmark function I ran in a Jupyter notebook. I really like this time it function because it's super easy to benchmark line. So here I was executing the for loop, and this ran in 33.8 milliseconds, sorry, ms, milliseconds. And then I was running the same code using the dot product, or the same computation using the dot product that I showed you before. So the second one here, that is the dot product, and it's about 22.4 microseconds now. So if I compare these two, running the dot product is about 1,500 times faster. And that is a huge speed up, given that if you look back, this is also more concise than this one. And of course, it's faster. So there's only an advantage here using a dot product instead of using a for loop in Python. So that is one of the, I would say, main takeaways when you use Python for scientific computing. Try to avoid for loops if you can, and see if you can rewrite something as a linear algebra operation. And so next I was trying to run this code on a GPU to see whether I can improve the speed further. So it was actually a quite good GPU. It was a 2080 Ti here that I used. So what I did now, I used Torch here. I was transferring the data onto the GPU with this code here. So 2 device CUDA 0. And this is just the first GPU in that machine. If I would have multiple GPUs, I can change the number. For example, I can change it to 1 to address the second GPU. I can change it to 2 to address the third GPU, and so forth. Here I was just using the first GPU in the machine, which is why there's a 0. Yeah, so I was converting the data or transferring the data onto the GPU memory here. And then I also set the benchmark flag to true, because otherwise the benchmarks can be a bit skewed, because things get executed asynchronously in GPUs. But so I was setting everything up correctly here. And then what I saw is that the computation is actually slower. And that can happen if you have, for example, these very small computations, because GPUs are quite powerful, but also they're not really good for these very small computations, because CPUs have been optimized a lot. And if you, so one CPU core is faster than a GPU core. Becomes in handy if you have a lot of parallel computations, if you have a lot of things that you can or want to run at the same time. Here I only had like these 3 values that I was running. So there, in this case, it's maybe not an advantage using a GPU. Where I really benefit from using a GPU is if I have very large computations. So here I have a matrix X and a matrix W. These are quite huge. And now Python ecosystem. And I must say I use these tools a lot because they're very convenient to use. And most of them have been around for more than 10 years. And they are very mature, and there's a great community, great documentation behind it. So it's still one of my favorite tools if I have, let's say, a regular, small, medium-sized data set. However, if I would work with a very large data set, I may benefit by using also GPUs for other tasks, such as classic machine learning. So there's this library, Rapids AI, or the Rapids ecosystem. It's ecosystem consisting of multiple libraries. So this is the library by NVIDIA that my co-authors work on. And here they implement a lot of libraries that also take advantage of GPU memory. So there's the QDF library, which is relatively similar to Pandas. However, here you use GPU memory instead of CPU memory when you implement the data frames. So you can also perform the computations on the GPU. And then QML, this is the equivalent to scikit-learn, and QGraph, the equivalent to network X approximately. And then these are already running on GPU memory, so there's no equivalent in Rapids there, but yeah, not necessary. And then there are also some visualization tools using GPU. So just I wanted to highlight that there are also alternatives. If you, let's say, plan to do deep learning, get a GPU, and then maybe you want to do some regular scientific computing or GPU machine learning, you can also use your GPUs for that using one of these packages. So while looking at GPUs, I was looking back at my book to see what or how the GPUs evolved over time. So I thought it was just fun looking at this. So this was a table I made in 2015, long time ago, about 5 years ago. So here I was comparing Intel, cutting-edge Intel processor, CPU, with the back in the day most powerful gaming graphics card, the 980 Ti. And you can see the main difference is, I mean, there are a lot of differences. GPUs have many more cores than CPUs, and that is related to the fact that, yeah, they are really optimized to execute lots of small computations simultaneously. And in terms of the throughput, you can see there are the floating point operations, giga floating point operations. So you can see that it's about more than 10, 12 times, no, maybe 15 times larger on the graphics card than on the CPU. So it's really a huge difference here between CPU and GPU. So now if we go from 2015 to 2017, so we see this kind of doubled. So we have now twice the throughput in terms of floating point operations when we go from the 980 Ti to the 1080 Ti. And the price didn't really change that much. It's still $700. It's very expensive, but it's still kind of reasonable. I will show you in the next slide some other numbers. So keep the 700 in mind. And now, just last year, Wahid and I updated the third edition of Python machine learning. And of course, things have improved again. So we are at 13,400 gigaflops now. But so the price also got more expensive, but you can see it's not a huge increase anymore. So here it kind of doubled, and here it's maybe 1.1 times as much. So it's not really improving that much anymore. And I'm not sure, but I would say maybe we are saturating GPU performance right now. So the trend right nowadays is more like, instead of using or buying more expensive GPUs, people try to do more on multiple GPUs. If you have deep learning models to compute or to distribute your computation across multiple machines and multiple GPUs, instead of just running one thing in one GPU. Back in the day, it was really hard to do that, but PyTorch and TensorFlow have evolved a lot in the recent years, and it has become much easier now to do distributed computing. There was just an update in PyTorch, PyTorch 1.5, like 2 days ago, where they also improved multi-machine training. Okay, so here's another chart, a benchmark I found at Lambda, which is a company selling computers. And I was looking a lot for benchmarks. It was the only good one I found. And what I wanted to also show here is that the most expensive GPU is not always the thing you should maybe consider buying, because it's much more expensive compared to what you get for the money if you compare to the baseline. So this is the baseline I had on the previous slide. This one here at the bottom. So this is the one for $1,100, and this is the baseline. And you can see there are cards, for example, Titan V, that is only 1.04 times faster, but when I remember correctly, this was like $5,000 or something. So it's like almost 5 times more expensive, but doesn't give you much more performance. So it's not always a good idea to buy the most expensive card. However, I should say this is so the RTX 2080 Ti is a video gaming card. So it's not really maybe optimized or built for being run 24/7. So maybe this one is just more robust in terms of how durable it is, and also warranty-wise. And also, just for comparison, there's a V100, which is one of the top cards, and it's $8,000, and it's only 1.37 times faster than the baseline here. So it's not always a good idea to buy the most expensive one, except maybe you're a big company, you have a lot of money, and you have space constraints or something like that. Okay, so anyways, so that is just about the technology trends, how GPUs evolved. But nowadays also people or companies are developing customized chips now. So not everything is focused on GPUs anymore, improving GPUs, because there are only really two big companies, NVIDIA and AMD. And AMD is, I think, a little bit behind on the software side for deep learning libraries. There was also just the PyTorch 1.5 version coming out like 2 days ago, and they improved the AMD ROC M support, which allows you to run PyTorch on AMD graphics cards, but it's not as mature as NVIDIA cards. In any case, I'm getting sidetracked here. So also what I wanted to say is that companies are starting to develop customized chips, for example, Google's cloud TPUs. And I think they are right now at version 3 or version 4 right now. So also that has evolved a lot. And ARM is also developing their own machine learning processors. NVIDIA also wants to extend the lead by improving GPUs. So this is more like tailoring GPUs towards deep learning, because back in the day, GPUs were more all-purpose cards for video processing and video gaming. So to make them more custom for deep learning also. And then Amazon also has their own chips again. So everyone is kind of developing their own chips. It's another trend here. But maybe enough about trends for now in terms of technology, in terms of hardware. Let us look maybe at trends regarding deep learning frameworks. So the tools that we actually use. So this is actually, I would say, a very sensitive topic and hot discussion. It's similar, if you remember, Emacs versus Vim. These are relatively old text editors, and people used to fight over them, which one is the better one. And it's also maybe a little bit similar to Mac and Windows and things like that, or Mac versus Linux and so forth. So there are pros and cons on both sides. Here I was just looking at what deep learning framework is most popular. That may be something useful if you are starting to learn about deep learning, which one you should choose. That's a very common question. Also, my students ask me a lot. I usually say doesn't really matter. Both are fine if you consider the two big ones like TensorFlow and PyTorch. But still, I found it interesting to take a look at the trends. So this is an article not too old. I think it was November 2019. And here, the authors collected citations from major conferences. So, for example, in Europe, CVPR, ICLR, ICML, and so forth. These are all the top machine learning conference or deep learning conferences. And the dotted line here, that is TensorFlow. So you, the dotted line here, where there's a solid line, which is PyTorch. And if you look at the dotted line, it's, in most of the cases, it's still going up, sometimes going down a little bit. But the trend is not huge. So in some fields, it's going up, so compared to before. However, what you can see is that for PyTorch, for some reason, it's becoming really popular. You can see it's really taking off at most conferences. So PyTorch seems to be what most people seem to use nowadays. I use both. So just recently, we had we are working on a research project where we implemented things in PyTorch, but then we also wanted to compare it to other models and make some modifications to those as well, and they were implemented in TensorFlow. So we had to also know TensorFlow in that sense. I was using TensorFlow a lot also for my book. We are using TensorFlow, and it's still one of the best, most supported libraries, so it's nothing wrong with TensorFlow. I was just looking at the trends here, which I found interesting. And just briefly how the data was collected. So they also excluded papers, excluding papers where the authors were affiliated with Google or Facebook, just to be fair. Because Google and Facebook, they are also publishing a lot now at the big conferences. So here, just to make the graph fair, they excluded papers that were from these companies. Okay, so in terms of performance, personally, I haven't seen a big difference. Couldn't really find good benchmarks. There was one comment on Reddit where people said that TensorFlow 1.0 is approximately as fast as PyTorch. Or similarly, PyTorch is by a very slim margin faster than TensorFlow 2.0. When you run TensorFlow in the non-eager mode, that is the static graph mode. However, people say that if you use the eager mode, TensorFlow is much slower, so they assume then TensorFlow 2.0 in the eager mode is much slower than PyTorch, which always runs by default in the eager or dynamic mode. But it's just anecdotal. And the only maybe somewhat good benchmark I could find was from Hugging Face. They are a company who are implementing a lot of transformer models. So they have a lot of expertise in transformers. And they did a benchmark, I think it was also on transformers, benchmarking transformers. And here, there's not a huge difference between PyTorch and TensorFlow. So for example, this pair here is on the CPU. You can see it's almost the same. And then for the GPU, for example, looking at this one, it's also roughly the same. So sorry, that is not the right one, this one. So there's not really a difference whether you use one tool or the other. So what is the difference between PyTorch and TensorFlow, and why is maybe PyTorch more popular? So one reason, I think it's maybe because TensorFlow 1.0 was a little bit clunky. So this is TensorFlow 1.0. So back in the day, we had to define the graph separately. So we had to define what computations we wanted to run, and then we had to initialize and evaluate the graph separately. And it was kind of tricky. I mean, you had your abstract definition here, and you couldn't really inspect it when you were running it. If there was a bug, it was really hard to find the bug. It was just tedious, I would say. So in PyTorch, they adopted a paradigm that was more similar to NumPy. So that's shown here on the right side. And this is more, like running NumPy code. You have the definitions, and you can directly run it and get the results immediately. You don't have to define the whole graph and initialize it and so forth. So I think that's maybe what people love about PyTorch, and what I certainly love about PyTorch. However, I should say TensorFlow also supports this mode now. It's just like TensorFlow 2.0 was maybe a little bit late, where a lot of people already started using PyTorch, which is why, PyTorch is maybe so popular nowadays. And also, I use both, and I really like PyTorch, I have to say also, because it's really, if you come from NumPy, it's very intuitive. But keeping a long story short, I also observed, or my opinion is that the deep learning frameworks are converging. So PyTorch is becoming more like TensorFlow, the static graph mode, and TensorFlow is becoming more like PyTorch. So they are somewhere meeting in the middle right now. So for example, here PyTorch added a lot of functions to implement static graphs, because in practice, static graphs are actually quite good for engineers if they want to implement things efficiently and optimize things and deploy things on mobile devices and servers. So that's actually where you want the static graphs, for example, in C++, and then you can export them. So PyTorch has a lot of stuff now to also construct static graphs, optimize them, and compile them. There are two APIs. There's also the C++ API, which got updated a lot recently in the recent update in version 1.5 on Wednesday. And the Torch script, which is a just-in-time compilation. So this is making PyTorch more similar to TensorFlow in a way that it also supports static graphs. It's of course optional, but it exists. And on the other hand, TensorFlow has the eager execution mode, which allows it to be executed dynamically like PyTorch. So in that way, there's not a huge difference between the two frameworks anymore. Both have static and dynamic graph support. Okay, I talked a lot about technologies now. So let me go over some of the challenges in deep learning. So one of, I would say, the shortcomings of these libraries, which are abstracting away a lot of low-level functionality to make them useful or easy to use for users, is that some operations are hard to compute or not efficient to be computed. For example, TensorFlow and PyTorch are centered around auto-differentiation for backpropagation. So you have reverse mode auto-differentiation, because you go from the error to the beginning to the inputs. So that's the backpropagation algorithm where you use reverse mode auto-differentiation. However, if you would like to compute, for example, higher order derivatives, if you don't want to use stochastic gradient descent, but you want to use or look at the curvature of the functions or the derivatives of the derivatives in that way, for example, the Hessian matrices, you would have, it would be more convenient to use forward mode auto-differentiation. You can use this the double backward trick. You can compute that just by computing the backward pass 2 times, but it's very inefficient. So it would be great if these libraries had support for forward mode auto differentiation. So you would then be able to compute higher order derivatives more efficiently. And that would then also maybe drive research into more efficient optimization algorithms. So there's this new library called JAX by Google, which also gained a lot of popularity recently. A lot of people adopted this library because it's very composable. It's very similar to NumPy or small operations. And then also on top of that, having automatic differentiation. However, I should say PyTorch also has that. So usually I also use that sometimes for teaching usually, but you could technically also use that for research. There's the Torch AutoGrad submodule. And they just recently added a functional API on Wednesday, in PyTorch 1.5, which makes this also more easy. And there's also Julia, for example, which is super nice, a super nice language, but I don't know, it's not very popular yet. And recently also Swift gained a lot of attention because I'm not that familiar with Swift, but I think it's more efficient to implement automatic differentiation in Swift. But to be honest, I'm not really familiar with Swift. I just saw there's a Swift for TensorFlow or TensorFlow for Swift coming up now, which people seem to like, people who tried it out, but I have not tried this, so I don't have that much experience with that one. But yeah, like I mentioned many times now, there was a major PyTorch release on April 21st, so just 3 days ago. And they also added the efficient computation of the Hessians, for example. I'm not sure exactly how that is computed. I'm not sure what approach they use and how efficient that is. I haven't tested that yet. But yeah, they are also, or PyTorch developers are also looking into that and extending the functionality of the AutoGrad submodule, having now this functional API, which makes it relatively similar then to JAX. Just, yeah, one thing to note. So what I said here is not really true anymore, so we can kind of cancel this because, so I'm not sure about the forward mode automatic differentiation, but at least the Hessian is now implemented. Okay, so another challenge is more related to not the library itself, but just how deep learning models work and weaknesses of deep learning models, and maybe one of the reasons why we don't see deep learning models in very high security related applications. So here was a paper, a recent paper, which I found really funny. So here the researchers tried to fool the Tesla autopilot. So they were projecting an image of Elon Musk here on the road, and the car autopilot in Tesla reacted to it. So it was braking suddenly. And the same way they projected the street sign here into the tree. So I actually have a zoomed in version here. So they projected a street sign into the tree, and the car was then also speeding up, basically. So this is really dangerous because you can imagine everyone, or almost everyone, could make such a projection on some object and then fool cars driving around. So that is maybe one of the reasons why we don't really adopt deep learning in systems yet that are very crucial, where there's a lot of risk involved when you, or danger involved if you make a wrong prediction, where you can't really trust the system yet fully. There are a lot of tools for performing such adversarial attacks. So here at the top, there are some tools. If you want to probe your model, if you develop a model and you want to see how robust it is to adversarial attacks, these are some of the libraries. And this is also a table from the paper. I won't go into too much detail about adversarial attacks, just want to highlight that these methods exist. And there are libraries for TensorFlow and PyTorch. So if you want to test your models with regard to adversarial robustness, you can maybe check out these libraries here. And you can see there are a lot of different attack mechanisms. Unfortunately, there are not quite as many defense mechanisms, but some defense mechanisms target multiple attacks. So even though there are more attacks than defenses, it doesn't mean that a defense cannot cover more or multiple of the attacks. So, but in any case, usually what happens if you use the defense mechanisms is that you also reduce the accuracy. So you make your model more robust to adversarial attacks, and then if you add maybe multiple of these defenses, you make it maybe really robust against attacks, but each time you defend your model, it becomes weaker in terms of the classification accuracy, which is one downside. So I don't think adversarial attacks is something we don't have to worry about, so it's still a very important topic. I'm not an expert in this area, but it's something you would definitely want to keep in mind if you are working on some application of deep learning where a wrong prediction has a high cost in terms of some societal, causing some societal harm or issues. So that was some of the challenges, also some neglected research areas where I just want to briefly highlight some things that are maybe not so commonly researched at the moment. So most of deep learning is based on classification in supervised learning. So in supervised learning, there are some applications of regression, and most of it is classification. One area that is not really, I would say, well represented in deep learning is ordinal regression. So ordinal regression is, in a way, you can think of it as classification, but you have an ordering information of the class labels. So you can think of it if you have a movie review. So you have a movie review, let's say from bad to okay to great. So you can assign a class label. You can say the bad movie gets a class label 0, the okay movie gets a class label 1, and the great movie gets a class label 2. However, you lose the ordering information. For example, if you have a movie that is bad, let's say this is your drawn truth label, and you predict great, so this is your prediction, you make an error. So now let's say you predict, this is my other prediction, you predict okay, it's also an error, and it has the same cost as this other one. However, I would say if the movie in truth is bad, predicting okay is actually better than predicting great, because okay is closer to bad. However, classification models don't take this into consideration because an error is an error, every error is treated equally. So ordinal regression would consider this information that there's an ordering that you go from here to here. So that means the loss between these two is smaller than the loss between these two, for example. And there are applications of such ordinal data. For example, I work a lot with collaborators in computational biology where we have molecules and we have measurements. You can also think of it as drug measurements, like the effect is measured on some scale from moderate to strong effect. And it's easier to work with data on such a qualitative scale, because if you use numbers and experiments were performed on different subjects or different labs, you would have to normalize everything. So in this way, it's more like a ranking data, which is very common. For example, if you also have a movie reviews and so forth, there are a lot of examples. So there was one research project where I worked a little bit on ordinal data, but there are of course several other ones. And I just want to highlight this is one of the neglected research areas. I just see we only have like 10 minutes left, so I maybe won't go into too much detail here. But if you're interested, the preprint is here on arXiv. So this was a method that was improving another method that had rank inconsistency. So another method had this rank inconsistency, and we improved this rank inconsistency and found that this improves the performance. So this was an age prediction problem where we wanted to predict the age of a person. And we were thinking of the age as a non-stationary process, because if you have a person, let's say a person is 5 years old, and there's a person that is 10 years old. The difference is huge if the person ages from 5 to 10. However, if the person is, let's say 70 and 75, the difference is relatively small if you look at the person. So here you maybe see huge differences in how the face looked. Maybe face features changed a little bit. The head became bigger because you're growing. But at this age, only the skin maybe changes a little bit. You have maybe some more wrinkles, but you don't look much different. So in that way, you can think of this as a non-stationary process. So there is not a well-defined difference between years. So here the difference between them is 5 years, and here also. But these 5 years and these 5 years are not they are not the same, basically, they're different. In normal regression, it's always the same difference, it's a metric difference. So that makes ordinal regression a little bit different from metric regression, from a, let's say, least square regression. Okay, yeah, and using this fixed version, we were able to improve the performance. So here's just for reference, CNN with regular cross entropy loss, that is just the normal classification. And on average, we tested on multiple datasets, but on one dataset, the mean absolute error on average was 3.39. And the lower is better, so that's the mean absolute error of the age, the true age versus the predicted age. It's quite good, so it's saying you are only wrong 3 years on average if you use the model to predict the age of a person. And then here, this is using another method, so you can see it's improved by about 0.4. And then going from here to here, it's another, I would say, less, but also 0.4. So here, this is our method where we fix this rank inconsistency. Anyway, so in the last 10 minutes, let me maybe go over some of the hot research areas. So one, I would say, hot research area is the transformer model, or transformer models in general, because there are many now. And I think Aurélien Girard talked about this already, so I don't need to go into too much detail of how that works. So it's based on this attention mechanism. And they are super popular, I would say, for like 2 or 3 years now. But there was one article that came out last year that was from OpenAI, where they said that they didn't want to share a model because it was too good and they were afraid that people could misuse it. So that was maybe one point in history where transformers really gained a lot of attention in media. So that was already more than a year ago, 1 year and 2 months. There were also, since then, a lot of improvements of models. And what is kind of scary, but also impressive, is that people, or here in this case Google, is scaling up the models to work on really large data sets, for example, 341 gigabytes of data. And the model they trained, or the chatbot they trained, Mina, it had 2.6 billion parameters, which is, I think it's a huge number of parameters. And these models are so huge that we as individual people can't even train them anymore. So you have to be a really big company. In a way, it's kind of sad that maybe one of the top deep learning models are only available to, let's say, a small number of people in this world. And also, I don't know, it seems like we're making improvements, but just increasing the number of parameters, if that makes the model work better, it's kind of sad if there's nothing better than just making things bigger and bigger and bigger. Because, I mean, at some point, we have to, I think, we kind of hit a wall when we maybe make things bigger, but at some point it doesn't help anymore. So it's kind of, I think, against creativity to just think about making things bigger. Anyways, so here is an example of the bot, what it did when it was talking to a human. And I think it looks pretty good, actually. So if you would talk to this bot for a longer time, you maybe notice that it's not a human, but I think it's getting pretty close. So it was having a conversation here. Hi there, what's up? And then the human complained about the Monday blues. So it's a Friday today, so we don't have to worry about that, at least. But then the bot said, I'm procrastinating on a paper I'm supposed to be writing. And that is something I would definitely say. So it is actually very human in that way. So I think that is quite impressive. But yeah, like I said, it's a huge model. It's not something anyone could train easily. So here's a timeline I found of transformer papers. So also highlighting the size of how big they are growing now. So they started, I think this is a million. So 2000, that would be 2.5 billion then, 2,500 million. So they started pretty small with 94 million. And then it's going up and up. So the GPT model was just 110 million. But then nowadays we have something like 8.3 billion parameters. So it's getting really huge. And the GPT-2 model that got so much attention was this one with 1.5 billion parameters. I think the Mina bot is not on here, but it would be bigger than that. It would be, what did I say, 2.6? So it should be somewhere here. And also another trend though is that finally research also try to make models smaller while maintaining the efficiency. So there's, for example, Roberta, or the Distilbert model by Hugging Face. which try to preserve the performance of transformers, but keeping them relatively small. And yeah, there are also lots of papers about transformers. Yes, I think these are only the BERT papers, the bidirectional transformers. Yeah, and one thing I just saw yesterday, actually, so that article came out like 3 or 4 days ago on Archive. So that was just an overview that researchers posted on the cost of training natural language processing models. And I found this quite a kind of upsetting that it's so expensive to train a model. And this is definitely something we just can't do as a single person. It's something only big companies can do. So for example, for 110 million parameters, you would already pay $2,500 to $50,000 in terms of just the computing cost that you need for that. So that's just the computing cost. And that is only training one model. So if you do research, you usually have to do fine tuning and you have to tune parameters, or you have to at least run it a couple of times. So this would add up. And this is really just, if you don't do any research on the model, you just implemented it like it was implemented in the paper. So if you would develop the model, you would need much more than that, which is kind of sad. Okay, so I had a brief section on how the attention mechanism works, but I think we are running out of time, and I think Aurélien Guérin covered this already, so maybe I don't have to go through this. Yeah, but just some fun applications of also attention that is not natural language processing. So here there's an application of attention to the alpha star model that is by DeepMind, where they implemented models to play StarCraft. And they were not able to, I think, beat the top world-class players, but they were very competitive, and that was a very impressive effort by AI or DeepMind to compete with human players in a very complex task. Okay, yeah, that's a strategy game here, just an overview. Yeah, and then there are, of course, like I mentioned, models that make things more efficient, where people try to reduce the number of parameters. So I think there's also the reformer model, when I remember correctly. The reformer model, I think they have efficiency but complexity n log n compared to, for example, regular transformer in terms of the cost. So there are improvements, algorithmic improvements also decreasing the number of parameters and so forth. So there's also an interesting paper, Transformer on a Diet. Yeah, so I don't think I have much time left. There were only a few things I wanted to say. So there's also one hot area of research in graph attention networks. I mean, this is just one application of attention mechanisms to graphs, but graphs in general are very popular these days. So that's also one area of research I'm working on. So here's a figure from one of our recent review papers. And graphs are especially useful if you work with molecule data. So in the center, this is a molecule. This was, I think, aspirin. And if you look at the molecule, it's a 3D graph. So you have usually coordinates, 3D coordinates, and there are connections. There are single bonds and double bonds, and also different atom types. The red ones are oxygens. This gray one is the carbon, and the white ones are hydrogen. And traditionally, what people did is they were converting the molecules into a so-called molecular fingerprint. So there was something like a hash function that was recognizing certain substructures in the molecule. For example, this position would correspond to this ring structure here, which is here. So it would assign a 1 if a substructure is present and a 0 if the substructure is not present. So this would be, for example, the keto group here and so forth. And yeah, that was one approach doing that, but of course, it is not a great approach because you lose the order. So you can't really say, or you can't really reconstruct the molecule from that fingerprint. And you can also have hash collisions. So it can be that you have different molecules in the same molecular fingerprint, for example. So in that case, it's not really ideal. That was something, though, where you could use a traditional machine learning, where in traditional machine learning, you usually have a table. In the table, you have the features x1, x2, x3, and then maybe some class label y. And then for each row, you have, each row is represented by one training example. So here, this would be the features of the first training example, features of the second training example, and so forth. And this is where you could use a molecular fingerprint, where each position is corresponding to one feature column, for example. However, this was not ideal because, yeah, like I mentioned, there were some shortcomings of this representation where you had hash collisions or same molecules mapped to the same, different molecules mapped to the same fingerprint. So one improvement was working with smile strings. Smile strings are strings you can extract, or from a molecule you can convert a molecule into a smile string. And this is very similar to a markup language like HTML. So there are certain rules, and I actually forgot how these work exactly, but I think these in parentheses are branches and so forth. So there are certain rules that you can construct a smile string from a molecule, and you can also go from a smile string to the molecule. You can go backwards, so that's fully reversible. But one thing I should say is you can't have 3D structures with that one. You can only have a 2D representation. So maybe going ahead, jumping too quickly here, but this would be the 2D representation of this 3D graph. So where you make everything flat. So the smile string doesn't preserve 3D coordinates, it only can deal with 2D molecules. And there's something like molecular conformers where you have, so you can think of it, you can rotate this group here, and it would be still the same molecule, just changing the 3D coordinates, and smile string wouldn't be able to capture that, for example. In any case, so smile string is not useful for docking, where you have to have 3D structures, where you want to dock a 3D structure into a 3D binding pocket. So that's where a smile string wouldn't work, but a smile string is still great if you want to analyze whether the molecule has certain properties, like if it's soluble or not, or toxic or not, and so forth. And this was where I was going with this. This is a text string, or just like text with characters, and that would be a great case for using an RNN model or even a transformer model, for example. Another approach for working with molecules was 3D voxelization, and that is, you can think of it as a 3D image in a way. Similar to CNNs, you would use a 3D convolution here. So instead of having a pixel, you have a voxel where you have a third dimension. And that would be a case where you use CNNs. But again, this also has shortcomings. And I would say the biggest shortcoming with that one is also that you lose the sense of, so this model is not invariant to rotations. So because you don't know whether you can put the model in like that or it's rotated, it's still the same molecule, but the prediction may be different. And also you have occlusion here. This doesn't really matter because you use the convolution, but it really depends on how your model is oriented, because different things will be adjacent to other things, especially if you have these 3D coordinates. So you would have to train the model on very infinite number of different conformations of that molecule to make this more robust, basically. So I think this is very expensive. That is one of the downsides. And I would say the most promising direction right now is using graph neural networks, where you encode this model directly as a graph. So there are many, many different models for this graph encoding. This is also something I'm currently working on. And if you're interested in graph neural networks, there's, for example, PyTorch geometric. I'm just showing you an overview. There are, I would say, at least 50 different methods for doing, or implementing graph neural networks, or having even different graph convolutional layers, and so forth. Okay, so I think we don't have much time left. Maybe just briefly mentioning self-supervised learning. That's another trend where people try to leverage data for supervised learning, but imagine a scenario where you have a lot of data, but you don't have the labels. So with that, you self-supervised learning, you would do something similar to transfer learning. You would pre-train the model on a related task and then train it on your main task. And self-supervised learning is called self-supervised because you would provide the labels by extracting them from the data set. You would use something that is obvious that you already have. In supervised learning, you would usually have a human providing class labels. Here, we usually look for a task where we can get the labels for free. So in this example, let's say you have images that are colored like this, and the task would be, the self-supervised learning task would be to color the images. So you would start with the colored images, these are your ground truths, and then you would remove the color, make the black and white version, and then let the network try to go back and predict the colors. So recoloring it, for example. And that would be one task where you can generate the labels, the colors for free, where you don't have to have a human labeling it because you start with the colored images. And there are other applications where you, instead of coloring an image, you fill in blanks. So you cut out regions from the image and fill in blanks. Or this one here, where you predict the context of a pixel frame. So you have, for example, this tiger here. You divide this into 9 regions, these green boxes, and then you shuffle them, and you just draw, or here you let the network reassemble them in the right order. So in that way, the network kind of starts to understand what a tiger is, because only if it understands what a tiger is, it can put the pixels in the right place, for example, or these super pixels. I'm calling them pixels, but they are more like patches in the image. And similar here in the second example, where you have a reference picture, so this one, and then you show it another picture that is related, and the network has to predict in which position it is, for example. So it's very similar. So here, not explicitly reorder everything, you have only a pair, but it's the same as above, essentially, the jigsaw. Okay, so yeah, with that, maybe the last topic, privacy. So there was also this recent article, April 14th, a survey that only half of Americans have decided not to use a product or service because of privacy concerns. So what they're saying, basically more, or at least half of Americans don't trust products because of privacy concerns. So even though we have now these very powerful deep learning models that are potentially able to enhance our life, we are a little bit wary that it collects too much data, or there are some concerns that it knows too much about us, and we maybe don't want to use it, or at least half of the people in the US don't want to use such products. Yeah, so one of my research areas was also then focusing on privacy. Of course, this is just one example. There are many people working on making machine learning more, let's say, trustworthy, or at least hiding information that the model shouldn't have or shouldn't need. So in this project, we have an application where we want to do face matching. We want to recognize a face. For example, if you enter a building, or you're at the airport and you scan your passport, and it should recognize that's you in the passport picture and on the camera, that these two people are the same. For that, we don't necessarily need gender information or store gender information or other types of information, because if you develop a database, this database can be leaked. Or let's say you have a video camera at a store, people may collect videos for security reasons, but you could extract all kinds of things like gender, age, and race, and do this for profiling. So in order to prevent that, the best way to prevent it would be not storing information about that at all, just having maybe information about matching. So you can maybe detect that there's a potential dangerous person in your store, but you wouldn't be able to extract all the gender information from everyone who visits your store. So with that, we developed some methods for removing certain attributes like age and gender and race and so forth. But this is just one application of privacy. There are many, many more. Yeah, so I think I should end this talk. This is my last slide now. So another challenge in deep learning is that a lot of data is still small. If you look at papers, deep learning papers, they are mostly working on benchmark data sets, usually image data, large image databases like ImageNet, but in practice, we have usually very small data sets. So not everyone has a big data set. So how can we deal with the small data problem? So one approach is transfer learning, where you pre-train your model on a large data set, and then you apply to a smaller data set, or you fine-tune it on your smaller data set. The other one is self-supervised learning, which is related to transfer learning, but you use the labels that you can extract from your images. So this could be, for example, pre-training on ImageNet. And this could be, let's say, on an unsupervised data set that is related to your data set, but you don't have the resources to label your whole data set. So you only have a small number of labels for your data set but you can extract the labels by, for example, these tricks I showed you before, where you color an image and do the jigsaw puzzle problem and so forth. Another one that is not frequently used yet is generating synthetic data. It's, for example, using a GAN or various autoencoders, variational autoencoders to generate new data for training model. And then one and few-shot learning. And then lastly, having a human in the loop, a human, for example, doing active learning, where you show a human certain examples, and if you're not sure, if the deep learning model is not sure, you ask the person maybe to label it. But of course, human resources are limited. You can't just label 1 million images, for example. So the algorithm would only ask the human about images it's uncertain about. But also there are tricks, for example, it's called active learning, where you try to learn from the training data in a way that is most efficient as possible, that you learn in a certain order. And there's also semi-supervised learning, where you use supervised and unsupervised data, where you first learn from a batch of supervised data and then also incorporate unsupervised data. Okay, but with that, I think I was talking too much. Sorry that I went over time here. So I think I'm ready to wrap it up. If there are any questions, let me minimize this and see if I can have it on my other screen. If there are any questions, so I'm happy to answer some. I think the problem is I still have problems hearing you for some reason. I think there's some issue with the microphone on your side. I don't know. It's unfortunate. It's kind of funny. I can hear myself now in your microphone. When I talk, I hear myself like 10 seconds later. There's something maybe about the internet also. Could be. Let me see if I can pull up the link to YouTube and see if there are questions on YouTube. Link to YouTube and see if there are questions on YouTube. Oh, there are no questions. Okay, perfect. Link to YouTube and see if there are questions on YouTube. But oh, there are no questions. Okay, perfect. But if you have questions later, yeah, just you can write me an email and I would be happy to answer. But there are no questions. Okay, perfect. But if you have questions later, yeah, just you can write me an email and I would be happy to answer. But there are no questions. Okay, perfect. But if you have questions, yeah, just you can write me an email and I would be happy to answer. But there are no questions. Okay, perfect.